can now start with our lesson 7. Let me double check first. This one. Where's this one? Okay. So today's topic is LAN and network layer. It's local area network and network layer. If you remember, your network layer should be in the OSI level number 3, because all people seems to need data processing, right? So it's physical, data, network layer, a data link layer, sorry, and network layer. So we'll try to deal with chapter 5, a bit of chapter 5, chapter 6, and do some IP address and subnetting. Okay, let's first go through some of the textbook information. So for local area network, we do have a bunch of them. Ethernet LANs, gigabit Ethernet, wireless LANs, token ring LANs. One thing to note about with Ethernet LANs is it's basically a standard. It's not really, oh, Ethernet LAN, oh, it's not a product. It's not a, like, something you buy right away. It's a standard. Ethernet LAN, then whatever cable that you need. Okay, and this standard is defined by the IEEE 802.3, I think. So more on that. Oh yeah. So it's basically used for computer network connections. For me, when I was growing up, I used to think that when I say Ethernet LAN, it's basically the blue cable. And I think about, oh, maybe the previous one, which we use for dial-up, I just call it telephone cable or dial-up cable. And then the coaxial cable that you use for TVs, I think about that as the cable connection, but basically they're all Ethernet LANs, right? Ethernet is basically the protocol or the standard. Again, protocol is like, oh, HTTPS for application layer, UDP, TCP, those are protocols. So Ethernet is also a protocol. And Ethernet is basically a protocol for local area network, which is a network or topology. So again, here's a quick visualization of what a coaxial cable is. One thing to note about compared to the other LAN cables is basically shielded, meaning you have maybe less, I wouldn't say 100%, less possibility that you get interference from other frequencies or electricity just because you have this tile shield, plastic jacket. And I don't have the picture, but at the end it has like a ring. And at the end it has like a needle. Ethernet LANs, so this is what I grew up with, the blue cable. It's basically the Cat5e. And another Ethernet LAN would be the Cat6. This is what you used before with the dial-up, with the modems. And they have specific, with the Cat6 as well, or the Cat5, they have different sub-genres, I say, subcategories. Like there's an RJ45, RJ whatever, and so forth. So also, now we're trying, week 6, we try to explain each layer. And now we're just going to focus on actually the network layer, right? In the 802.3 standard by IEEE, basically your Mac client and the media access control themselves all belongs to the data link layer. Just something good to take note. We also enter again with the topologies, but let's give some different explanation this time around. With the bus topology, you do have a contention-based protocol. It's called CBP. And if you Google contention, it just means that it's competing for resources. because only one signal can pass at a time. And that's because, that's why we have this phrase called listen before talk. So it's like when I'm talking, you guys stay silent for now, or else we can't really communicate at the same time. So think of it like that. Next, we enter again with the star topology, and we all know that now they can communicate easily, more easily. However, if you kill the hub, everything goes down. So this one is single point of failure, brings the network down, and the packet flow all passes in the hub. So again, packets is where you have your data and you segment the data into data units and you put other stuff there and it becomes packet. And now you send packets, and then until the other node or the computer or the device receives it and now tries to rebuild it and make sure that it's the same. So if I send you a document, it's gonna be in packets, and when it comes to you, it's gonna be rebuilt again to form the Word document. So the difference between frame handling in a hub and a switch. So if you have frame, Ethernet hub basically would send frames to all the ports. Again, frame is just another way to classify the data in the network layer. If we call it packet in the other layer, we call it frames in this layer. And then again, in the Ethernet hub, with the hub, we send it to everything, everyone receives it. In the Ethernet switch, only the recipient would receive that. So there's an illustration of collision and broadcast domains. A quick thing to note about collision domains is basically you have two devices sending packets in the same network. Hence, there's collisions. Okay? Broadcast domain, all ports on the hubs and domains are in the same domain. Basically, you send packets in the same domain. Classification of Ethernet switching, you have the port capacity configuration, frame forwarding method, highest layer used for forwarding. So for port capacity configuration, we have two. We have the asymmetric switch and the symmetric switch. For the asymmetric switch, it allows you to connect between ports with different data rates. So if you have 100 megabytes and the other one has 10 megabytes, that's fine. But if you want to do the symmetric switch, your connection between ports should have the same data rate. If it's 10, the other should be 10. If it's 100, the other should be 100 as well. Frame forwarding methods, different ways. You have store and forwarding switching. It means you want to store everything first before you forward it. That's why it's store and forwarding. That's why it says here, it receives entire frame, then forwards. Cut through switching is basically it sends the first 6 bytes. If it's good, you try to keep sending. So you send it in frames. Again, when we say again in packets, in frames. So those are data units. Fragment-free switching checks the first 64 bytes before forwarding. And as this image in the textbook that we have, you can easily visualize if this is your frame, your store and forward range would basically try to receive first the whole frame before forwarding it. The cut-through range would only need until the destination address to send it first. Fragment-free range already comes to the table, which is the data. Does not need the whole data, but at least it includes the source address and the length. So virtual LANs, it made it possible to have a lot of networks in a single physical network. So what it does is basically it divides single existing physical network into multiple logical network. So logical is something virtual. It's not really physical. Logical networks of each which forms its own broadcast domain. So advantages of virtual LAN is, again, cost reduction, performance improvement, ease of management, because you also have tools that you can easily see what's happening in your virtual LAN as well, like an interface. Enhanced network security, flexible user location, better use of network resources. So right now the standard is people just use virtual LANs. Here's a diagram of port-based VLAN system. You have the router, your switch, and 2 VLANs. You have this one with the router, 2 switches, and 2 different VLANs as well. So like with this diagram, when a user moves to another port, the network administrator must reconfigure the VLAN membership, which can be time consuming, particularly when moves are frequent. Wireless LANs. Physically wired interface replaced by air interface, Wi-Fi. So the architecture for this one, as defined by IEEE 802.11, you have the physical layer and the data link layer again. And a while ago you have the MAC client, but right now you have the logical link control with still the MAC, the medium access control, and all of the different protocols defined by the physical layer as well. And they also define that there should be minimum spacing between frequencies so that maybe they don't collide. Or remember when you're listening to radios as well, if you did not put in the right frequency, you get also the other signal from another radio station. So that's what they're trying to avoid, to have like a spacing of 25 megahertz. Okay. So the architecture of IEEE 802.11, the wireless LAN is the ad hoc mode and infrastructure mode. The ad hoc mode is very, I strongly remember this just because I showed you last week when I was playing all the time with local friends or my siblings. We just basically hit this wireless LAN and we can play without even an internet connection. So ad hoc mode looks like this. So there's no wires, that's for one. Don't forget it's wireless. And if there's a basically a defined range where it can only meet. One thing to note that because of the way this is set up as well, as you can see, A and B can communicate, B and C can communicate. However, A doesn't know C and C doesn't know A, so it might be, let's say, just so happens B is already getting overloaded with communication, or let's say bandwidth frequency, but A doesn't know it. So that's one of the things that you have to look out for when you're configuring. This one looks a lot going on, but this is how your house connection would look like. You have the internet, and now you have the router, wired LAN, and then you have access point. So now most of us would see the Wi-Fi router, which you connect that and it works for everything already. But this one separates with the wired LAN and the access point. Think of it with this is your like Wi-Fi router. Now your devices could use that. So let's say you're in an office space, or let's say classrooms, right? I can't just have one router in the school and everyone connects to it. The better way to implement it is basically I have, again, the internet connects to, let's say, wired LAN, whatever, and then underneath here connects to a wireless access point, and in the next classroom, let's say there's another wireless access point, so that we, in this room, we get a good connection instead of like me reaching that wireless access point out there. Okay, so if you're in your house, try to really avoid that. You put a router like so far from your room. Let's say you use your laptop in your room. It's so far and there's a lot of like walls. It's gonna be, you're gonna have slower internet, basically. Okay. We come back to the logical architecture of the token ring network. It's like last week as well. So every node passes to another node just to communicate with another node. If node 1 wants to communicate with node 3, it has to pass to node 2. Okay, let's see. So it has two things. It has a priority field and the reservation field. Priority field basically indicates the current priority of the token. This operates as follows. So when a station wants to transmit a priority in frame, it must wait until it can capture a token whose current priority is less than or equal to 10. So that's just basically the priority standards that they use. Another thing is for reservation field. So when a data frame goes by, a station can try to reserve the next token by writing the priority of the frame it wants and send it into the frame's reservation bits. So station is basically your node or computer. Frames reservation bits, basically you also manipulate the frame so that it would know the priority for that one. Physical architecture of token ring network enables the network to overcome one of its early criticism of the hub, the star topology, that the failure of any one station brings the network down. So with that, by having every station connected to the panel, it's easier to bypass the switch at the panel to switch out any station that fails. So this is switching rather than using the hub. Okay, so we move on to IP addressing. It's quite a lot, but we'll just enumerate them. As you can see now, we have store diversion, IHL, DHCP, ECN, total leg, flag, protocol, title lead, header, checksum, source address, destination address, option, padding. We'll quickly enumerate them and just simply define. So again, version basically stores your version IP number. Could be IPv4, could be IPv6. A quick difference with IPv4 between IPv4 and IPv6. IPv6 has more IP addresses that you can assign. IHL is the number of 32-bit words packet header. Again, that's think of it's like your metadata. And that's called the IP header length. Next is the DHCP. It's called Differentiated Services Code Point. You define the quality of, this should be off, of service. ECN is basically explicit congestion notification. It does end-to-end notification of network congestion. Total length, it just shows you the packet length in bytes. Identification just identifies which packet frames it belongs to. Flags control or identify the fragments. Fragment offset, it just shows where fragments belong. Time to live, time packet is allowed in the network. You can say that, oh, after 10 seconds, it should be already deleted from the network. Protocol, ID number of transport protocol used. There's ICMP, there's IGMP, TCP, UDP. And if you remember before, as you said, we have the TCP and UDP, the transmission control protocol, which It's slower, but you receive feedback. With the user datagram protocol, it's faster, but it doesn't give you feedback, and they have different use cases. Checksum, we encountered this word again. It's basically for your error detection. Source address, basically you need to put that information as well where it comes from, and the destination address is basically where the final destination of that packet is. You have options as well, so there's other options that the sender could include. Padding, ensure packet header is a multiple of 32 bits. So let's start going over the muddiest point. Would it be simple to avoid collision domains simply by using a switch rather than a hub? If so, what benefit would a hub over a switch that is worth risking collision? So I Googled, and they said that for most part, the general consensus, they're saying no. And a lot of the things that we're doing, like the bus, the star, could be, some of them are not really used a lot anymore, but it's good to know because it's the foundations where you build other designs as well. So again, going back, for the most parts, you don't really use hubs anymore, right? Well, hubs are also known as repeaters, meaning that they basically echo whatever is coming in to a given port out all other ports in the domain. So yeah. So again, that's why switch was created, because of the failures of hub. What is the difference between a distance vector routing protocol and a link state routing protocol? So as defined, the distance vector sends their entire routing table to the directly connected neighbors, while link state protocol sends information about directly connected links to all the routers in the network. So distance vector gives all the routing table, link state only the directly connected links. I heard that IP addresses were run out. How do people solve the question? So IPv4 only have around 4 million IPv4 addresses. So one way they try to fix that is through subnetting, because before, when there was maybe no standards yet, is people think that, oh, you have your own IP address for your computer, it should be unique globally. Oh, you also have your IP address for your computer, it should be unique globally. And we have millions of devices so this would get consumed right away. Hence, we only have the network ID. So think of it, your home. In your home, you do have your router, and that's connected to outside, right? And that router has its own public-facing IP, which is unique globally. But inside of it, all of the devices that's connected, it has an IP address that may be similar to other people in a different router. Okay, so let's say at your home, you have a unique IP address for your router, but when it connects to your computer, you might have the IP address same as my IP address in my home computer as well. Okay, so that's one of the ways they try to solve it. The other thing is moving to IPv6, just because they have million, trillion, I don't know how to calculate it. It's basically 2 raised to 128. Okay, so that's a lot. That's a lot. IB version 4 addressing. So last time we did this exercise. If you're given a 255, you basically grab everything, expand it. You start with 0, 1, 2, 3, 4, 5, 6, 7 with a base number of 2. Raise that to that number in their exponent and just add them up. So the maximum you get is 255, and the least that you can get is 0. Okay. So Now we try to go into IP subnetting. IP subnetting is in the OSI Model 3 network layer. It divides networks into subnetworks to simplify network administration as well. And you can easily locate a problem in the network. So again, this is what I told you. Imagine all computers connected to the internet with their own IP addresses. It will be chaos. So here's how it looks like. So if you have an IP address here, you basically can create subnets. And we'll talk about this later on how to do that. So you can define subnets and assign them to different devices. Could be computer, could be printer, or I don't know, other devices such as mobile as well. So with IP subnetting, just to show you the diagram a while ago. So if you are in your, this is, let's say, device. They have their own IP, and think of this box as a router. It's the router that communicates to the other router, and it's the router that would communicate inside with the devices. And just don't forget, the router is also called the default gateway. If you've done your IP config command or something like that, you should see default gateway as well. And you should see an IP address for your router. So before going deep dive with that, in the network layer, we do have the TCP IP. You often hear that all the time. If you build a simple project or your app, before you even deploy it online, you try to test it locally. And if you access that through your network, it's TCP IP. Okay, so again, with TCP IP, once the device have found each other through Internet protocol, the TCP will define how will they talk. So it will define like how fast would they transmit, so what language would they use, things like that. And with TCP as well, they have this windowing. It's basically a process of sending data in packets. Okay, so this is windowing. So what it tries is, first it sends one packet first and wait for the ACK, the acknowledgement. So only send one packet. It's just to test that if this device B or computer B exists. Okay, or yeah, if I have a connection for that. Once it transmits and gets the acknowledgement from B, it now will double and send two packets. So now instead of one packet, we have two packets now. The number or just the sequence. And if that transmits and also gets the computer A gets acknowledgement, it will now double again. So it will double and double until it reaches the maximum. However, if let's say during packet 10102, you got an error, A would try to resend it back to B until it can receive. Again, you can also define how many times you would resend. Let's say I would only retry connection 5 times and end the connection or transmission if that doesn't work. So again, in this case, it tries to send the packet 102 again to B, and once it's done, it's gonna go back again to sending one packet at a time. So think of it like when you're driving a car, you're accelerating, right? Accelerating fast, but when you hit your brakes and get to a full stop, you'll go back to being slow again before it becomes fast. Okay, so IP address. In IP address, you also have the subnet mask. Subnet mask enables you to logically segment a network. good thing to note is it's to prevent a device from communicating to one another over a physical network. So if you're connected to, let's say, your router at home physically and another computer is connected there physically, what you're trying to do is preventing them to talk. It does not make sense in a home setting, but if you're in the enterprise level, you have a lot of network connection. You definitely don't want one computer talking to different departments, like sales department, HR department, so you try to isolate that now with subnet mask. You only want them to communicate with one another and maybe just have one device that communicates outside, right? So, as I mentioned, default gateway, or as also known as router, before it goes to the default gateway, your computer will first look at in your local network. So if you're in your house, if you're connected to a network, a router, a wireless router, it will first check if the one that you're trying to connect to is that another computer, is that another printer. It will try to find out. If not, it now goes to the default gateway to check if it exists there. And that's the point that the default gateway, as your router, as your access point to the internet, will now check in the internet. So let's say you hit www.cityU.edu. Again, this is to show you a big circle, you're in one network. The small circles are your devices. And this small square is your router or your default gateway. So again, let's say this in the upper circle, it tries to find that, oh, is CityU.edu in my network? No. I check the router or the default gateway, and the default gateway will now go to the internet to look for it. Okay. Might be that simple, but IP address, again, still in the IP address. If the IP protocol cares only for the IP address, where are the domain names come from? So going back, let's first backtrack a bit when we said that computers. So what do computers understand? Machine language, right? One is machine language. It's basically ones and zeros. So how would they understand this? That's the question. It's basically text. So with that one, we now entered with this domain name system server, or DNS server. So what it does, basically the router will communicate with this one and says, hey, do you happen to know the IP address of CityU.edu? Okay. And then the DNS server would respond with, this is not true, okay? I would say that, hey, I do know the IP address of CityU.edu. Here's the IP address, and gives back this example number of 192.145.42.2. And now the computer is able to understand that. Okay? So one thing to quickly put that in your memory is DNS server is just the phone book of the internet. Okay? And this one, to just explain the steps before it really goes to the domain name system. So before it asks the DNS server for the IP address of, let's say, CityU.edu, or in this case, my LinkedIn profile, there's a few steps that it can do, right? First, it would check, does your browser knows this? So your Chrome cache, or not Internet Explorer, Microsoft Edge, the cache, it will check first if the browser has this, if they store this information. If not, it will check your operating system. So even your operating system stores information. So do I already know where this is? Okay? If it does not know, it would now proceed to query the router, and it will ask, hey router, do you know what is CityU.edu? What's the IP address? And if the router doesn't know as well, it would now connect to the ISP provider, and basically the ISP provider should now, if they know it as well, if not, they would now connect to a DNS server. So these are just the steps that's happening in the background. Let's see. Here's just an example of, oh, it's dark. So I took a screenshot of my system settings in my Mac, and as you can see, when I click DNS, I do have my own cache. So these are IP addresses you can't see, and these are domains. Domains are the URLs. So also, I guess we can cut for now and take a break before I proceed. So the next half, the second hour would be more of this, and let's do whiteboarding again, okay? We'll try to recap the Octet binary to IP address, and then now continue to subnetting. So take a quick break. Please don't get sick, and most people are sick, so don't get sick. See you 10 minutes plus. So we left with DNS server, and we'll continue with TCP IP. This is another screenshot from my computer. So again, with your IP address, you can definitely configure it manually. Configure your own IPv4 address, get your own submask, your router IP as well. This could be okay for personal use, but if you're doing it, let's say for the school, for the business, and you have a large enterprise or medium size, it's gonna be very much of a big hassle to manually configure this for every device, right? So yeah, manually assigning IP will not work with huge networks. So the way we can automate that is basically introduce DHCP. With DHCP, you can give an IP range that it can assign. It can also, basically the IPs are leased, meaning it's just being like rented, right? And one thing to note about is the lease is renewed once it reaches 50% of the max lease time. So if you configure your DHCP to say, hey, give that device IP address 192 blah blah blah, and let it be valid for 10 days. By the 5th day, it will now check again with the router if it's like, oh, can I extend this IP address? And it would say yes or no depending on your configuration as well. So DCP, keyword there is dynamic host control protocol. So in your computer as well, you can just hit using DHCP, and now these are locked and you cannot edit them. They automatically assign them for you, and you can renew them anytime you want, or let them renew by their own. Okay. Also, this is a topic that would connect with what we're saying about you have your devices in one network, and your router, or what we call the default gateway, is the one who connects to the internet. So that was the solution, is basically to create the network address translation. So it's, let's say your home router has an unique global IP address. Once it goes there, it will now translate and find that certain device that requested. So basically that's what's happening. So let's say you have two different locations, two different routers, two different houses. The cloud basically would see that, oh, this is unique IPs, But now once it's in the router, let's say there are other devices, other IP addresses, the network address translation would now find which specific device is the one requesting for connection to, let's say, CityU.edu. Oh, same slide. Okay, this is a quick recap before we go to our whiteboarding. So last time we mentioned about Octet. Why is it called Octet? Right? A tutor is the OCT, so like octopus, right? Octagon means 8. So last time we defined with the IP address, if we convert it to binary or bits, we do have 4 octets. So as you can see, we have 1 octet here, another 1 octet here, the 3rd octet, 4th octet. So you basically have 8 binary numbers. And just to refresh you guys, so 1 octet would have 8 bits, okay? A bit could represent basically 0 or 1. It's basically true or false, on or off. Think of your light switch. So as we represented this last time already, so if you're gonna use, let's say, the value of 32, basically need to turn the switch on. You give that value of 1 to say that, hey, it's true that I used 64, or I used 128 and 16, something like that. So with this, we always try to, if you want to calculate manually, the easiest one is grab a paper, whiteboard it, instead of creating your own program, or Googling, or doing online calculator. But basically, here's how you form your octet, is you start at the rightmost, you assign 1, then times 2 becomes 4, 8, 16, 32, 64, and 128, which is the 8, right? So a recap again from last week. If you're given with an IP address of 192, 168, 9, and 1, you would definitely see this again. The bits, the first octet, we only need to use 128 and 64. That's why it's true and true, or 1 and 1, and the rest are zeros. And in this case, the second octet, we only need to use 128. So 168 minus 128 is 40. So you can't use 64 for that. You can use 32, so you put it in true, or 1. Now you only have the value of 8. You can't use 16, but you can use 8. Now you put that true, and the rest is false. For third octet, you have 9. Put zeros until you see 8. Put that to true, and put the last one, which is 1, to true as well. And the fourth octet, the easiest one is you have 1, basically false on everything except for the last bit that has the value of 1 to make it true. So this is how the IP subnet mask looks like. Maybe you guys have seen it sometime, right? If you were checking your IP or checking your configuration setting for some reason, you could have seen this 255, 255, 255.0. And if we convert that, it's very, very easy as well. 255 is the max, meaning all is true for octet 1, 2, and 3. And the fourth one is just 0. Okay? And in subnet masking as well, we do have what they call the Class A, Class B, Class C. So what are those? So when we create a subnet mask, we first want to define how many networks you can have and how many hosts you can have, devices. So meaning I could have more networks, right? Or more devices. So let's say the networks are the tables and devices are the people inside of it, right? So if I have, let's say, 2 tables and I have more people in those two tables, I would definitely need to reduce the number of networks that I want, which is this one. So if the red line goes towards more to the left, it means you have less networks, less tables. However, you would have more IP addresses for more devices, in our analogy, for more people. Okay? So if we just contrast this first with C, this is basically saying that I have more network, more tables, but I have fewer IP addresses that I can assign to devices or people. Okay? So quickly go back to class A. I think we mentioned that. So if it's 255.0.0.0, you definitely have this representation. Everything is true for the first octet. Second, third, and fourth are 0. Class B, it goes until the second octet. And as you can see now, it's here, the middle dot. And the last class is class C. Hence, this is the reason also that you can see it in your laptop, computers, because you don't really need to have a lot of devices for that. And the last one is the zeros. So another notation that they show us, if you've seen it in the internet, or like when you're deploying applications in the cloud, AWS, Azure, whatever, sometimes you would see this /24/12, okay? Again, network ID, this is not yet it's not the device's ID. When I talked about, again, the tables, think of the network ID as the address of the table, not the people or the devices, okay? And this is a notation called classless interdomain routing, so CIDR. So once you see an IP address / number, that's a CIDR, and it basically gives you an easy way to see what is the subnet mask. If I have this network ID and I have a /24, you start from the left, you count 24 once or through. So this is 8, another 8 is 16, another 8 is 24. That's why you got 24. You got 24 bits that are turned on through, or is as a number of value 1. And if you represent that with the IP address, it's going to be 255.255.255.0. Okay? So, now there's a simple question. Let's say you're given the other way around. You have a mask. You have a 255, 255, and 248, and /21. Just think of a /21 first. You go from left to right. You get 8 plus 8 is 16 plus 5 bits. And that forms your 21. Okay? So, going back first, when you have equal, let's say this is 8 or 16 or 24, it's easy because you just cut and everything here is 0. However, with 21 now, you have in your third octet having true values or 1 values and 0 values. And now with the mask view, let's say, oh, find the network ID given the device's IP address, which is 192, 168, 40, and 55. The first thing you would do before any computation is my first octet all ones. If that's true, I don't need to look at 192 because I know it's included because everything is used. I look at my second octet. Is everything in ones? Yes. Now for the second octet of this device, I know it's also used. However, when I go here, the third octet of the device, if you compare it with the mask of the third octet as well, it says, oh, I've used only 5 bits. So now you have to first check if your third octet's IP address, so what does it show? It does show that it only uses from 1 to 3 or 5, so here as well. So you can say that, oh, it's included. But once you have something here, a number here, you would not include that. To just maybe clear that up a bit is basically, you can have an IP address that says that, oh, that's your network ID. But let's say you're given a device IP address of, let's say, 0.42, and you try to cut this and there's value, you would say, oh, the device IP address is 0.42, but the network ID is 0.40, something like that. Okay?
Let's see if there are more exercises. Oh, no more. So let's do the whiteboarding stuff first. Let's try to quickly recap this, and I'll give you examples with, I'll definitely guide you with subnet and explain it along the way. So let's say you're given with a number, just 172.
So quickly form your groups and whiteboard time. Try to switch partners. Go up. Yep, stand up. So with this, give me the 4 octets of basically the bits. Give me the zeros and ones. Yep. Zeros and ones.
For the 172, not 113.
Yep. So if you don't remember doing it, just create the 1, 2, 4, 8, 16, 32, 64, 128 first. Create that table and you should be able to get it. With this very easy practice, please don't Google, because we already did this last week and there's already a guide here in front. I just pick a random number, so I'll check. For first sequence?
Yeah. 128 plus 32 plus 8 plus 44 plus 72.
Okay, minus that one, you get 4. And then this is the next. 22. 12. This is the next. And yeah. You know what to do?
I think we're going to use a calculator, sorry.
Okay. Okay, maybe do the second.
Oh, okay.
Yeah.
There's a really cool graphic marker.
Okay, good, good, good.
12. Oh, so it'd be 0, 0, 0, 0, 0. So we want to get the small number, and then so we need any of these two numbers added to all, which would be equals 4. So that would be 0, 0, 0, 0, 1, 0, 0,
Easy, right?
1, 1, 1.
Pretty easy.
So now we're second.
Let's see. This is the subnetting part. Let's see if I. See if there are examples.
got it?
Another marker.
Oh, you can borrow. Okay. I think everyone got it.
That's good. That you guys don't need the guide on that. Oops. Let's see. Go back. Too easy. Okay, let's do something like this.
Give me the 4 octets, I mean the binary numbers, if I have slash
19.
Just for the 19 or for the whole thing?
So in this one, what's my binary? No. It's not gonna be the same.
I don't understand the slash.
So slash, basically, to recap, it's a notation with the CIDR. It basically helps you right away with how many bits are turned on, starting from left to right, continuously. So with that, if you're given a network ID and a CIDR, you should be able to get this. That would give you your subnet mask. Again, going back, it's way easier than what you did actually. So, what is the 24 first?
You go left to 24, right? Or is it right?
How many ones are these?
8.
How many ones are these?
8.
Oh, yeah. That's
How many ones are these? Yeah.
That's
So,
all?
yeah.
So if I go 19,
So was the answer just 3?
So you just counted how many ones of this number of ones?
Yeah, so that helps you get this. Now I say get this and also get your subnet mask.
Okay, so
I need marker.
Plate's flat.
I'll get you more.
or in a while. It's easier, right? Than the
I have a question. So this is that IP address is the 19 one. What is this address for?
So there's three things. So you have the network ID, you have the device ID, and the subnet ID, subnet mask. All of them are in the IP address format. Okay. So given this network ID, how would you find the subnet mask ID given this location? So that's
So
how
the
it should be.
subnet is the slash.
Yes,
That's the subnet.
it would
So
define.
the three, what are three?
You have network ID and device or host ID, basically the computers, whatever. The computer.
That is the normal IP address.
This is an IP address format, and IP addresses are used in many ways.
Okay. So device, network, and the third one is?
Subnet mask, is that what I missed? Device.
The network and device.
Yeah, host. You can also call it host. So your network ID is think of it to what the router has or what the router ID is for the router, and then you have a subnet mask. Is it because we want to use the subnet mask to have basically divide your network ID by host ID. Now to do it? Okay.
Yep. Very easy, right? Should ask harder question next week. Let's see. Okay. So this is cool.
You find a harder question?
Not really hard.
Harder.
Yeah. Okay. So I'm gonna use this, so no cheating. Let's go add something. Okay, so there's something. Now let's put this. Let's quickly do this. So I wanted to add something else. So let's say you're given a mask. 255.255.0.0. Okay. And now you have a subnet of, let's say 1. Subnet. And question is, how many hosts? But before that, I'll quickly explain. Remove that. 2 dots.
What are the hosts?
Oh my god. Host is basically is basically the devices.
Let's say computer, printer, things like that. And your network ID is the network, that the big circle that I showed you a while ago.
Okay. Yeah, so before that, sorry. Let's quickly see this. Blah 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 blah. Yeah. So one thing to note about when you're computing your number of hosts. Okay, I copied this. Number of hosts. So when you have, let's say, this number, right? Your only usable. Oh my god. Usable host is only gonna be 254. The reason for that is when you create a subnet, your first and last would be reserved. The first is for identifying, and the second one again was what was it again? Oh yeah, yeah, correct, yeah, and broadcast. Thanks. So it means that given this one, what would happen is, oops, this IP address of 255.255.0, that's the first one, it's used for identifying, okay? And then the other one would now be used for the last one, sorry. The last one would be used for the broadcast domain. So again, broadcast the data. Okay, broadcast. So the way you would we would know the number of hosts is basically this formula. Okay, let's now remove that. The formula is 2 raised to n minus 2. Let's do this. Raised to n minus 2. Why minus 2? Because again, first and last would be reserved. Okay? Okay, so going back. Number of bits. Okay, and now you would ask what is n? It's basically when you convert this back to bits, it's basically the number of bits. Okay, so when you start with this, how many bits we have again here? 24, right? It's going to be 2 raised to 24 minus 2. Okay, that would be your number of hosts, meaning the number of devices that you can, no, the number of IP address that you would have that you can assign to a host. Okay? Okay, so going back, given with this mask and a subnet of 1, how many hosts do we have?
C.
65534. Oh, 65534. So that's the answer. Another one. Let's use the next example here. Let's say you have 225.128 subnet 2. What's the answer? Okay. As we talked before, when we have a mask, we have the class A, class B, class C, right? And I would be saying network ID and host ID. Subnet is your number of networks, number of network IDs. Host is your number, host IDs or devices. So right now, so given this one, if the first one, I think the first one, let me fix that one. This should be 0. Yeah. Okay. I'll explain the 3 things that we answered, and I'll let you fill up the other ones. Okay. So if you're given a subnet of 1, meaning we only have one network, your mask is this one. How many hosts do you have? Right. So what happens here is you have 16 bits, right? So it's going to be 2 raised to 16 bits, which you have this one, and minus 2. Okay? Because it's 1, doesn't matter for that. Now, here, we also have 16 bits. But because the subnet, as we defined a while ago, Put here, just to note it, third octet, something like that. Quickly make that smaller.
So based on this first one, it already gave us that this is a class A, B, or C? B, correct. So class A, 0, 0, 0, and class C is only 1, 0. You can never have all zeros or all 255 because that doesn't make sense. So given with class B, okay, when you said like, oh, I only have one subnet, so you don't do any division, you get this number of hosts. Now come here, you're gonna ask, so what's the 128 for? Well, you still have the 16 bits, and now with this one, you have 1, 2, 3, 4, 5, 6, 7, 8. You have the 2 bits, which is, oh no, sorry, 1 bit, right? Which is this one. And it means that this would signify your subnet. Okay? Given this bits of your how you convert stuff, okay, you only need 1, right, to get the 128. Okay? The formula to get your number of network or subnet is basically 2 raised to s, meaning this value. 2 raised to 1 is 2. Okay? If we go back here, we did not use any bits for our subnet. 2 raised to 0 is 1. Okay, I repeat. So given this mask, we have 16 bits. That's why we have 2 raised to 16, which is this one. 2 raised to h, 2 raised to h, yeah. No, not this one. You're gonna get confused, sorry. So with 2 raised to 16, you get 65,534, right? And you divide it by subnet. The question is, how do you get the subnet? With your third octet, let's focus on the third octet. You have this, right? How many bits did you use? None. And the way you compute your subnet is 2 raised to, how many bits did you use? 0. 2 raised to 0 is 1. So now 25534 divided by 1 is still 36, then minus 2. Okay? Now we answered the next one. We still retain the raised to 16 bits, but now we have the 128. And 128 is basically having 1 bit, which is true. Now to find out how many subnet you have is basically 2 raised to how many bits that you have 1, right? 2 raised to 1 becomes 2. And now we would have the 65,536 divided by 2 minus 2, and we'll get the 32766. And the last one that we did was this one. So we still have 2 raised to 16. However, our third octet is 1, 2, 3, 4, 1, 2, 3, 4. A total of 8. So now, to know our number of subnets, it's going to be 2 raised to 8. The bits in your third octet. Right? 2 raised to 8 would be 256. So now, when we do this again,
we'll have 65,536
divided by 256 minus 2, we get 254.
And let's quickly bring up that calculator for the last one before I let you do the rest. So if I have 2 raised to 8, 256. Okay? Now I said before, first 2 raised to 16 because we have the class B.
Class B is this one. Okay? It's your class B.
25536. And you now divide 256, get 256 minus 2, 254.
So I hope that was clear, and because I really want this to be correct, so please let's do another whiteboard and fill up the rest. And once you fill this up, you would notice that, oh, these are the only masks that I can have with this class B, right? So again, let's try to use the remaining time to somehow master this. Let's do whiteboard again. You can go ahead and create a table and copy this first two and the last one and fill up this 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 6 entries. This time around, I'd like everyone to do it individually because it should be easy. Let me go more individually.
This one. 2, 2, 0. Don't forget your minus 2. Okay, you got it.
Okay, good. Got it? Awesome. So, just to summarize this one, we've been using this to divide, right? So, now if you add back 2 and multiply it with your subnet, you should always get the same number of IP address that's available for everything, right? So, that's why I would say multiply, because again, let's say you have 256 network times 256 hosts, you would still have the pool of the total pool of 65,536, right? Because we just minus 2. So all of this, each and every one of them has the same total of 65,536 without the minus 2.